Welcome back. We are on the next lecture, and up here on your screen you can see we're looking at DeMorgan's theorems or DeMorgan's laws and bubble pushing. So we're still in chapter 4 of the book here, and we just went over some of the binary, hexadecimal, and decimal number systems. So now we're going to talk about this law, and we're going to make this a short lecture and just stick to just this right here. So again, the material that we're going over is very important. You can still build electronics without it, but it's actually really nice knowing this stuff because it allows you to optimize your simple circuits and at least know this this kind of math exists. All right, for Boolean algebra. All right, so let's get right into this. So DeMorgan's theorem, DeMorgan's law. What they basically say in a nutshell is this. They talk about if you have the sum of products or the product of sums, you can turn these formulas into either or. So if you have something based on a sum of products, right, then you could turn that into a product of sums, right? And then the simplest form of it is this right here. And there's two different formulas or two different equations. And so remember, the bar just means inversion. So typically we'd draw the bar over things if we could, but it's too hard in the text, too much editing. So we're just going to leave it like this. So what this says is this is x and y. So the invert or the not of x and y is equivalent to not x or not y. And similarly, the invert of x or y is equivalent to not x and not y. All right, so that's very hard to understand when I say it, but if you look at it, so basically if you were to invert either, so this is a product and this is a sum. If you invert a product, then it's the same as the sum of the variables inverted. And if you invert a sum, it's the same as the product of the variables inverted as well. Graphically, and so let's look at it graphically. Graphically, what it says is that if you have an and, right, which is, and then you invert the output, that's equivalent to an or with the inputs inverted, or if you like it without the inverter symbol. If you have a NAND here, right, it's equivalent to this right here, all right, which is an or with the inputs inverted. All right, that's all there is to it. So what it allows you to do is it allows you to convert AND gates to OR gates or OR gates to AND gates as long as you have inverters, right? So we call this bubble pushing. And so these little bubbles, right, which represent knots or inversion, you push them. So if I take this bubble and push it through this AND gate, it turns the AND gate into an OR gate, but then the bubble gets replicated on both inputs, and here it is here. So I push the bubble through, the gate turns into an OR gate, and then we have the bubbles on the inputs here. Okay, so that's what this looks like. Now, before we go on, I wanted you to take a look at the Wikipedia page for this. So if you just Wikipedia search for DeMorgan's laws, you can read about it. So he's Augustus De Morgan, a 19th century British mathematician. All right, and what this is really all about, this is more has to do with set theory. All right, and the set theory can be applied to binary because binary can be thought of as a set where the set is 0 and 1 and that kind of thing. And so if you look up and you read a little bit about set theory, if you haven't done it, there's a couple words, conjunctions and disjunctions. They mean OR gates and AND gates. So a conjunction is like an and a disjunction is like an OR gate. All right, so we can find these analogies to things. All right, and then here's the math right here. So if you remember in set theory, U means union, and remember the upside down U means intersection. So this is interesting. So what this says is it says that the if you were to take the negative, right, or the invert, the complement in set theory, right, that's that bar. So if you take A union B complement, that equals A complement intersect with B complement. Likewise, if you take the complement of A intersected with B, that's equivalent to A complement union with B complement. And then they show it graphically over here. All right, so this is exactly, we can map this into the Boolean space with just two values, 0 and 1. And then you can go through some of this. It's just set theory and logic notation. And if we go down far enough, we'll see under engineering, there it is. So A and B not is equivalent to A not or B not. Additionally, A or B naught is equivalent to A naught and B naught, and that's exactly what we have here. All right. So you can read through this, but that's basically the gist of it. Is just these two simple formulas can be mapped into a Boolean logic. Okay. All right. So DeMorgan's laws, what they help us do is convert AND gates to OR gates to AND gates, and they also help us do optimization because we can simplify things by, say if you've got, for example, say you've got a circuit you've designed and it's all AND gates except for one OR, and you're like, God, I just wish I could get rid of this OR. You can. With DeMorgan's law, you can convert the OR into an AND as long as you have enough inverters, all right? And we'll take a couple examples. We'll look at that on the blackboard in a minute here. All right, so again, I'd like you to read through this, but I'm just going to kind of go through this. So here's another example. So this is saying that z equals x and y, right? And we've just got the bar over there. Just showing graphically the bar is the notation that you would normally use. And there's physically an inverter there. This whole thing creates a NAND gate, right? That's equivalent to this right here. All right, and again, the exact same. Z equals x NAND y, z equals x NAND y, all right? Or you could say z equals x and y inverted if you want, but that is the NAND gate, all right? So if we discretely have an AND and an inverter, that's the same as a NAND gate, all right? Now, when you're designing little combinatorial circuits, so we've learned that there's ORs and ANDs and NOTs and XORs and so forth, and say you're designing a little circuit, and it's like when one signal is a 1 and one's a 0, or this other signal's a 1 and this one's a 1 and this one's a 0, then I want to output a 1. That's a combinatorial circuit. You've described like an if clause, right? An if clause in a C or JavaScript or something. And that's the kind of things that we want to be able to implement in electronics with basic gates, with basic logic gates. So we have this concept of a sum of products and a product of sums. So sum of products simply is like a big OR list, right? So z equals x and y, or a and b, or f1 and f2. So see, sum of products. So the products are the ands. So these are your and terms, all right? And then it's all ORed together. And you've got one big Boolean expression that's going to output a 1 or a 0, all right? Now, so you've got this thing right here, and now you've got AND gate. It requires AND, and it requires an OR gate, right? But maybe the gates that you have don't fit this, right? So you could apply DeMorgan's law to this. And so we can't change the meaning of this. So if we were to invert this, right, that would be incorrect. But if we invert it twice, it would be the same. So what we'll do is we'll invert it twice. We'll use DeMorgan's law with one of those inversions, right? And then we'll leave the other inversion there. So in other words, it's like if you want to do something to a number, you can surely multiply it by another number or add a number, but you better divide and subtract if you want to be equivalent, all right? So it's like doing algebra. You want to maintain the value, but you can play around with it to transform it. All right, so if you take a look here, this is what's happened. So I've parenthesized this expression. Then I've said, let's go not. So not is going to give us back the original value, right? Okay, so we haven't changed the value, but now we can play with DeMorgan's law, which states that if we have a sum of products or product of sums, it's the same as, equivalent to, if it was a sum of products, now it's a product of sums with everything inverted, or vice versa. Here, we've got a sum of products. So now we look down here. Now take a look very carefully. Look what's happened here. So x plus y turns into x plus y. A and B, or A times B, turns into A plus B. And F1 times F2 turns into F1 plus F2. But we need to invert each one of these. So notice the inversions on it, right? The inversions. So now this is equivalent to this. So let's say, for example, we have a 3-input, let's say we have a 3-input AND gate. So this would be one expression here, one expression here, one expression here. Each one of these, so we've got to AND this, and then we need one OR gate here, one OR gate here, one OR gate here, and then we would have a bunch of inverters, then invert the whole thing, and it would be equivalent to this. So the whole point is you can transform logic using these rules into different forms that might be easier for you to implement with the gates that you have, all right? Okay, so let's move on here. and then this is showing what's exactly happening there. So we originally had this right here graphically, and you know what? No one can figure this. If you just look at this going right over your head, right? It went over my head when I looked at it. You can't keep track of it, but you do it graphically, and then it's pretty easy. So this is the exact same circuit, but now graphically. So here's what we began with. All right, and then notice I've got one OR gate that's 3 input, and then I've got 3 2 input AND gates, right? That's what this represents. This is X, Y, A, B, F1, F2. Here's X, Y, A, B, F1, F2, all right? And then I OR them all together. Well, what if I don't have those gates? What if I have a bunch of OR gates and then I've got a 3 input AND gate, right? Well, we can use DeMorgan's theorem on it. So here we go. So this is what we got. So I'm going to add 2 bubbles to it, 2 inversions. The result is still going to be the same, right? So that doesn't do anything. But I kind of hold this one off over here, and then I process this one. So I push the bubble through the OR gate, so the OR turns into an AND. Then what happens? Then I get a bubble here, and a bubble here. All these get inverted, right? Then I push those bubbles through, and then it turns each one of these into an OR, and then I got bubbles all in the input. So now, and then I've got our other bubble that we had here, right, because we only pushed one through. So now we've got this AND gate here, right, and with an inverter on it. So it's really a NAND. We need a NAND, so we assume we have inverters, okay? And then we've got all these OR gates with all the variables inverted on the input. So now it's equivalent to this, which is just what we computed mathematically. So I typically do this graphically, right? After I figure out what I want, kind of with logic, I'll do it graphically so I can see what I'm doing and not make mistakes. All right. So anyway, so that's what DeMorgan's law is used for. Now, here's the opposite: a product of sums. So here's a sum, and there's a product of the sum. Okay. Again, exact same thing, right? Now we just put 2 inversions on here. We bring one of the inversions in, and then we apply DeMorgan's law, and then everything just flips. So now it's a sum of products. So there's a product, all right, and then it's a sum. But remember, we got to invert these variables. Now, key thing here, notice B already had inversion. B had an inversion. So now B's doubly inverted, so now it's just B. So now when we simplify this, look at that. So now we have this, and B is just B. So inverted, 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 but B is doubly inverted, which just is B, okay? You don't have to write the double inversion. So there you go. So there's that example, okay? And then again, here it is here, a product of sums. So we had this scenario. So when we designed our circuit, we designed it and we have an OR gate, we got an OR gate, we got an AND gate, and we're like, we don't have that. We've got a bunch of AND gates and like only one OR gate. So we say, okay, well, let's use DeMorgan's law on this. So again, we add our 2 bubbles to it. We push one bubble through, the AND turns to an OR. Now we got 2 bubbles here. The bubbles come here. We push those bubbles through. That turns both of these ORs into ANDs, and then we have bubbles all on the inputs. Here we go. So now we got AND, and then this is an OR with an inverter on the output, which is a NOR, right? Okay, so we can call it an OR, or we can call it an OR with an inverter, or we can call it a NOR. And then here's our inputs, and then notice B is no longer inverted because it got doubly inverted, right? And so now there's B. So now we've got a sum of products again, all right? That's DeMorgan's laws. That's all there is to it. So it's really important to just know that these things exist. So when you go designing a circuit, and some people think in one way, like they think in terms of this expression, or this, or this, or this, or maybe you're thinking and this, and this, and this. Just like when you write code, right? If you write code, you can do it either way. And it works in code too. So if you're doing programming, right, and you have if A, and B, right, that's the same as if not A or not B. Try it. I guarantee it'll work. So it allows you to invert things, and then now here's the kicker. Say you've got, talking about computers, say you've got a computer architecture that can evaluate ANDs or ORs differently. Say that an AND or a compiler. Say the compiler generates a lot more code when you have conditional logic that has ORs in it. So the compiler and maybe even the processor architecture likes AND expressions. So if you could transform as much into AND expressions, that's way better. That's going to get you faster compilation and faster code execution. So that's another reason why this is important. And also, sorry for saying the word and, but you have to. Additionally, the actual gates themselves could have a different speed. Let's take a quick look at that. Let's take a quick look at that just for curiosity's sake, all right? So let's go here and let's look at a 74, let me see if I have this, 7408 is a 2-input AND gate. All right, so we'll take a look at one of these. Now remember, modern technology is LV or LVC, so we're not going to look at that. We're going to look at older technology. So we'll look at a Texas Instruments good old 74 LS08. And what we're going to look at is the propagation delay. All right, propagation delay. All right, so this is unsearchable, I believe. Yeah, because it's graphic. So let's go back up here. We'll just have to go to the data sheet here. And all right, so what I'm looking for is the propagation delay and electrical. Here we go right here. So this is a T propagation, low to high and high to low. What that means is if the AND gate is high, how long does it take to go low? If it's low, how long does it take to go high? Typically it's symmetrical, but sometimes it's asymmetrical. So it's showing here that a low to a high is 17 nanoseconds and 27 nanoseconds maximum, but a high to a low is 12 and 19. It's faster, which is interesting. So we'd like to spend our time going high to low. In any case, the bottom line is we've got a 17 and 27, a 12 and 19 for the AND gate. All right, so 17, 27, 12, 19. Remember that for a second. Let's go look at an OR gate, a 2-input OR gate. So a 2-input OR will be 72 LS 32. Again, let's look at Texas Instruments. So we're comparing apples to apples. There we go. Okay, 2-input OR. Again, these chips are so old, they're graphic. This is a bitmap. It's been scanned in, you can see. Let's scroll down here. Again, shows the circuit design. If you're crazy and want to build this, aha! So this is interesting. So the low to high and high to low is 10 and 15 and 14 and 22. On the other one, look at that. It was 17 and 12, 27 and 19. So 15 and 22, 27 and 19. So one of these is faster. Which one is that? This one is. So the OR gate is faster. So if we can do something that uses more OR gates, we want to do that because we're going to have faster propagation delays and we won't have to wait. Those AND gates are slower. So this is why knowing this stuff is very, very important if you want to do crazy level optimization. So again, say I'm doing something, say we're building a computer and we're building a circuit and we've got a microcontroller, all right, like a Raspberry Pi or an Arduino or whatever, and we've got some circuit and we know that the processor is going so fast and we want to do this computation electronically, we want to do something electronically, we look at the propagation delays, we're going to add them all up and we're going to say, wait a minute, we won't be able to do this because when you add all these propagation delays up, it's going to be too long. It's going to take too long for how fast this processor is going or whatever. We got to do it faster. Well, wait a minute. Can we turn our ORs to ANDs or ANDs to ORs? Right? And yes, we can with DeMorgan's law. And then in this case, in the LS technology, the OR gate is faster. Maybe in a different technology, say LV or LVC, the AND gate is faster, right? So you would look at that. But this is a level that if you want to get down and optimize, you need to know this math and these things so that you can do that. And again, just know it. Just know that it exists so you can say in the back of your head, I know I could make this faster. There's some law or something I read. You can go back and always figure it out. But if you don't know this, then some other person can make this circuit go faster. And you're, how are you doing this? That's what happened when the Apple II computer was made, right? Or the Apple I computer, Apple II computer. It was so optimized. Steve Wozniak optimized that computer so crazily. Just every day, he was like, I can get rid of one chip, I can get rid of one gate, I can do this. People could not understand how he put so much into so little. There's like so few chips on it compared to these other computers with all these boards. This is how he did it. And that same way of thinking, that same paradigm works today with anything, with code, with electronics, you name it, you can still optimize it, all right? And that's important to do. All right, so let's go back to our text material here. All right, switching standards and logic families. So let's go ahead. We've talked about this before, so we're going to go through this pretty quickly, but let's go ahead and stop here. And this is a good place to stop. DeMorgan's laws, remember them, and play with them and experiment with them. And we will come back in another lecture and start on this other material. So I'll see you in the next lecture. Bye.